Like alkanes, cycloalkanes also have conformations. Remember that conformations are structures that differ only through the rotation around single bonds. Of all the possible cycloalkanes, we're going to focus in this highlight video on cyclohexane. We focus on cyclohexane because it is very common and because it has very discrete conformations that we can analyze. So in this highlight video, we are going to learn how to draw conformations of cyclohexane, and we are going to learn how to predict the relative stabilities of different conformations of cyclohexane. And these different conformations are called chair conformations. Let's think about the structure of cyclohexane. If we take it straight out of the paper like we draw it, it would look something like this. However, planar cyclohexane is very unstable. Okay, so why would that be? Well, there's really two reasons. One is that if we look around this ring, we see that all of these carbon-hydrogen bonds are eclipsed. So we have many eclipsed bonds, and we know that this adds up to torsional strain. Okay, so this makes the molecule unstable or less stable. The second reason is that if we look at the bond angles, the carbon-carbon bond angles, so let's just pick one from this carbon here, we'll see that these bond angles are not what we would expect for an sp3 hybridized carbon. So there creates angle strain. Okay, and that's when the bond angles deviate from the ideal bond angles for a given hybridization. So these bond angles would like to be 109.5, but they're actually 120 degrees. So that also leads to instability. How could planar cyclohexane become more stable? Well, the way it can do that is by bending out of the plane or rotating out of the plane to generate different conformations. For cyclohexane, what happens is that each of these carbons rotates either up or down. So for example, this carbon could rotate down, the one next to it would rotate up, down, up, down, up. So they're alternating up and down. And what we get from that is a ring structure that looks something like this. So notice that this carbon here is rotated down, and that's this carbon right here is pointing down. And then it went up, down, up, down, up. All right, so this type of structure is called a chair conformation. So what do we call it that? Well, people have imagined, I guess, that this ring could just sit in this chair like this. I always think about it as if this was actually a person. So this is the body, here's his arms, and his feet come off here. Would be sitting in this chair or chase lounge or something like that. Why would the cyclohexane adopt this structure? Why is the chair more stable than planar cyclohexane? All right, so there's really two reasons for this. The first is that notice that all of the bonds are staggered. Okay, there's no eclipsed bonds anymore. And the second thing is that the carbon-carbon-carbon bond angles all become 109.5 degrees, just the ideal bond angle for sp3 hybridized carbons. So this cyclohexane ring is really a very stable structure. Notice that there are two types of carbon-hydrogen bonds. There are those that are going straight up and straight down. So let's highlight these. One up, one down. They alternate carbons as we go around the ring. Up and down right here. All right? These ones that go up and down are parallel to an axis. If we put an axis in the middle and we rotate this ring around, so these types of bonds are called axial. Okay, so there are 6 axial bonds. Those bonds are connected to hydrogens in this structure. The other bonds that we see are those that go out around the side of the structure. So we have one here, 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 and here. If we think of the orientation of these bonds relative to the axis, or if we think of this ring as being a planet Earth right here, rotating around the axis, then where would these bonds be close to? Right? They would go around the middle of the Earth. They'd go around the equator. These are called equatorial bonds. All right, so cyclohexane has 2 types of bonds: axial bonds that go straight up and straight down as long as this ring is horizontal, and equatorial rings that stick out around the sides. Drawing cyclohexane is a little tricky, but I'm going to give you a series of steps here that are going to help you to do that. My steps are just slightly different than what are in the textbook, but I think if you follow these, it'll help. All right, when we draw the cyclohexane, we are going to draw 3 pairs of parallel lines. All right, so the first set of lines, we'll start over here on the side, are going to be sloping up to one side. The top line is shifted up a little bit over the top of the bottom line. The second set of parallel lines are going to go off of the ends at roughly 90-degree angles. So they're going to go up and they're going to go down. And the third set of parallel lines are going to connect the rest of the structure. So here's the ones we've already drawn. The last ones are going to connect here and here. So notice that the red lines are parallel to one another, the blue lines are parallel to one another, and the black lines are parallel to one another. So to draw the other types of bonds, if we want to draw the axial bonds, off of every one of these bonds, if these two are pointing up, then the axial bond goes up. If they're going down, then the axial bond goes down, and they alternate up and down around the ring. Now when we draw this, the bonds in front, or on the lower edge, are in front. Notice that when I drew this last carbon-hydrogen bond right here, I made a gap because this bond, it's coming from the part of the ring that's behind, and so this bond is behind the one that's up in front. Now the trickier bonds to draw are the equatorial bonds. And so the way that I think about them, I'm going to draw them right here, is that these bonds are going to be parallel to the carbon-carbon bonds that are 2 bonds away. So if I'm going to start here on this carbon, I would count this as bond 1, bond 2, and so the new bond is going to be parallel to that bond. All right, so that's going to put this bond here, this bond here, this bond here, this one here, and this one is going to go here. All right, so there's all of our equatorial bonds. So if you're drawing cyclohexane, we can now add in hydrogens to all the bonds around the ring. All right, so cyclohexane has 2 different chair conformations. So let's draw the second chair conformation. We're going to do it just the same way, but we're going to start with the first 2 lines sloping up to the in the opposite direction. So I'm going to draw those 2. We'll do it stepwise here again. I'll draw these at 90-degree angles to the first lines. And then we'll close up the ring with the last set of parallel lines. Now, an interesting thing happens, like we saw in the video, is when we do this ring flip, all of the bonds that were axial in the first structure become equatorial, and all of the equatorial bonds become axial. All right, so now our axial bonds are going to be in blue. They're the same bonds that were in blue in the structure to the left. All right, and our equatorial bonds are going to be red. One more, like this. All right, and now we could fill in all of our hydrogens. So make sure you practice drawing these cyclohexanes, because you will be asked to do this on an exam. So the faster and neater that you can do it, the better you're going to be. Let's see what happens if we add a substituent to the cyclohexane. So in this case, we're adding this methyl group right here. We'll have methyl cyclohexane. So I'm going to draw it the same way. I'm not going to do it stepwise now, but our first 2 lines will be up like this. The next 2 will be at 90-degree angles, and then I'll connect up the ring structure. So when I do these structures, what I'll do is I'll draw the ring, I'll draw all of the bonds, axial bonds and equatorial bonds. And once I've done that, I will then go back and place the substituents. All right, so there's all our bonds. So now what we want to do is place a methyl group onto this ring. Okay, let's do this in blue. The easiest place for me to place a group is going to be on one of the end groups. So right there is a good spot, and I can choose to put that methyl group on either the equatorial or axial bonds. Let's start off by just putting it here on this equatorial bond. Let's fill in the rest of the hydrogens. And here's one of the structures for methyl cyclohexane. All right, so the next thing we would want to do is draw the structure that is generated by the ring flip. All right, so remember, we do this one just the same way, but we start by angling our bonds to the opposite side. All right, and then what we do is we add in all of our bonds. I'm going to add in the axial bonds. This one's behind this time. The axial, the equatorial. Remember, the equatorial are always going to be parallel to other bonds in the structure. and then we can place our methyl group. So now one thing to remember, notice where we put the methyl group before, that is the bond, the carbon that's furthest to the right in that chair structure on the left. So that position, if we draw our ring right, is going to be the furthest to the right in the other structure. So that carbon is going to be this carbon as well. Notice that the methyl group is on a bond that points up, and it's going to remain up in our structure on the right. So it was in an equatorial bond on the right. It's going to be on an axial bond on the left. So remember, like we saw before, every bond that's equatorial in one structure becomes axial in the other structure, and vice versa. Fill in the hydrogens, and we'll be done drawing our structure. So these are the two chair conformations for methyl cyclohexane. So what do you think? Would one of these be more stable than the other? All right, in one case we have this methyl group in the equatorial position. And in this one case we have it in an axial position. All right, so they aren't the same energy, of course. Here are some structures I generated on the computer, and notice this is the axial methyl group. This is the equatorial methyl group. And in the axial methyl group, these hydrogens on this methyl group become much closer to the axial hydrogens on the other side of the ring. In fact, we call this, if we count this as carbon 1, we go 1, 2, 3 over here, or if we count the other way, 1, 2, 3, we call these 1, 3 diaxial interactions. And by pushing those close together, they create steric strain. Okay, and steric strain makes the molecule less stable. So on this little graph on the left side, it shows two positions. Here's one of the conformations, and here's the other conformation. The lowest energy conformation is set at 0. That turns out to be the structure with the methyl group equatorial. The one at the top, the higher energy, is the structure with the methyl group axial. All right, so this is just a rule then, okay, is that the cyclohexane is more stable with substituents in the equatorial position. All right, and the difference here, says on the left, is about 5.7 kilojoules per mole. All right, so let's more complicated structure. Let's dive right in and do this tri-substituted cyclohexane. Notice that there's 3 different methyl groups on this cyclohexane. So when we put more than one substituent on a cyclohexane, we end up with some different possible relative directions. So notice between these two, we have one methyl group that's pointing up, because it has a wedged bond, and we have one that's pointing down. These two are on opposite sides, and so we call this arrangement trans. Okay, so we essentially have one methyl group on one side, the other methyl group on the other side. These two are also one up and one down, so these two are also trans. And we could look at these top two. These are on the same side. Same side. We call this cis. All right? So let's draw our cyclohexane, our chair conformations. So just like before, we'll start in the same way. I always tend to draw this one going up to the right first, but that doesn't really matter. Okay, let's draw this chair. Okay, then we're going to add in the axial bonds. And the equatorial. Then we want to add our substituents. So let's just count around the cyclohexane ring. I'm going to count just like we would name this. I'm going to put a 1, 2, 3, and 4. Notice we have methyl groups on 1, 2, and 4. And I'm just going to arbitrarily decide that I'm going to put the first group here. So that's 1. This is going to be 2. This is 3. And this is 4. All right, to make it easier, whatever I have going up on the structure above, so if this says up here, I'm going to make that methyl group up on my chair conformation. So at position 1, I have a methyl group, and out of the 2 possible bonds, this bond is going up. Position 2, the methyl group goes down. So here's position 2. We have an axial bond going up, equatorial going down, and so this methyl group is going to go down. And at position 4, we have our methyl group going up over here, and so that up is axial. All right, let's fill in our hydrogens. And there we go. So notice, okay, this one is down and this one is up. If we look at the relative positions or directions of these 2 methyl groups, notice that one is up, one is down. This is trans. They're on opposite sides. If we compare this methyl group to this methyl group over here, we have one going down and one going up. Likewise, this is trans. Okay, just like we had up above. And if we compare this methyl group to this methyl group, notice that both are pointing up, so they're on the same side, and so this is cis. All right, these arrangements don't depend on whether those methyl groups are either axial or equatorial. They only depend on whether they're on the same side or on the opposite side. Let's draw our other chair conformation that's generated through a ring flip. Okay, we start the opposite direction, and we generate our ring. We go through, we put all of our bonds, axial bonds, and equatorial bonds, all right, and then we place our substituents. Now the tricky part here is to realize that this position where I put position 1, notice that it's the carbon that's furthest to the right in the ring structure on the left. Okay? That position is going to remain the furthest to the right in our new chair conformation. So that's going to be this carbon over here. The methyl group on that position was pointing up, so it's going to remain up in our new chair conformation. So this is going up. So position 2, this was 1, so this is 2, 3, 4. Our methyl group at position 2 was down, so it remains down. And our carbon at position 4, our methyl at position 4 was up, and so it remains up. Okay, let's place the rest of our hydrogens. Like that. Now let's just check it. Okay? Now the cis and trans relationships need to remain the same. Okay, so if we compare this methyl group with this methyl group here, one is up, one is down, these are trans. Okay, just like they were before. We compare these two, this one's up. We have one that's up and one that's down. These are also trans, just like they were before. And this methyl group to this methyl group, both are up, and so these are cis. All right, so the last thing we want to think about here is which of these structures would be more stable. All right, so let's look at where our substituents are. In the structure on the left, we have two methyl groups that are equatorial. We have one that's axial. In the structure on the right, we have one that's equatorial. We have two that are axial. All right? So the structure over here is going to be more stable because more of the methyl groups are in equatorial positions. So make sure that you practice do a lot of these drawings and analyzing the positions, making sure that each of those bonds that come off the ring are in the correct angles and directions.